All right, welcome everyone to the GOCC. Before we get started, I want to remind you of our community agreements that we are all learning. Everyone has something to contribute and no one has all the answers, not even the speaker. Today, I'm excited to introduce Santiago Estupinan, and he's going to tell us about a new shifted Littlewood-Richardson rule. Take it away, Santiago.
Thank you. Thank you very much for the introduction. Thank you to the organizers for the invitation. It is a pleasure to present here. This work on a shifted Littlewood-Richardson rule is a joint work with Oliver Pechenik. And so let's see first a bit of background. A symmetric function is basically a formal power series over countably infinite indeterminates. Its main property is that you can permute its indices and that leaves it unchanged. Some examples of symmetric functions are the homogeneous symmetric functions, the elementary and the power sum bases. And as you can see, by permuting the subindices, you obtain the same function. Just a convention, whenever I index a symmetric function apart from the Schur functions by a partition, this means that I am taking the product of this symmetric function indexed by each of its parts. And the main symmetric function that will be important for us in this talk is the basis of Schur functions. These are very important because of their connection to representation theory. Here is an example of these functions, but I will provide an example that describes this in more detail. And so basically, to calculate a symmetric function indexed to a certain partition, in this case, the partition is 3, 2, you construct this diagram that has two boxes. Sorry, I think this should be the partition 2, 1 instead of the 3, 2. There is a typo there. But so once you have the partition, in this case, 2, 1, you construct a diagram consisting of two boxes in the first row, one box in the second row, and you're going to fill the boxes of this diagram with integers in such a way that they are increasing in rows and columns. In the rows, they can be weakly increasing. In the rows, they have to be strictly increasing. And all possible such fillings correspond to each of the monomials of these functions. So for instance, the tableau in item A is the one corresponding to the monomial x1 squared x2. And all the monomials come from such a filling. And the connection between representation theory and these functions comes from the Frobenius character or the Frobenius characteristic map. Basically, once you have the character of a representation, and a character is a function that captures all the important properties of a representation, you can recover all the fundamental blocks or irreducible representations from the character. So for a character phi, the Frobenius characteristic map associates this symmetric function. Again, in this case, P sub lambda is the power sum symmetric functions, and the Z sub lambda in this context is just a scalar. Once you consider this characteristic map, and if you let chi to the exponent of lambda represent the irreducible representation corresponding to the partition lambda, then the Frobenius characteristic map sends this character to the Schur function indexed by that partition. And so this is the connection I was alluding to before. Then if you can understand the change of basis between Schur functions and the power sum basis, you can recover all the information from the irreducible representations. Now, all I have said so far is for linear representations. And so what is a linear representation? As you may recall, this is a homomorphism between the group that we are representing and the group of invertible matrices of a certain vector space. But instead of considering linear representations, you can consider projective representations. And the main difference is that instead of representing each element of the group as a matrix that is invertible, you allow it to be represented up to a scalar multiple of the identity. And then you obtain a projective representation in this case. And perhaps this notion is not very well motivated. So there are different ways you can kind of justify this notion. In physics, for instance, if I am not mistaken, the Hilbert space or the different configurations that a Hilbert space can take can be identified with a projective space. And then if you are interested in acting on this space using the symmetric group, something that is very common in physics, you are interested in studying the projective representations of this space. There is also an algebraic motivation that maybe is more natural for mathematicians. So there is this problem of classifying all G representations of a certain, like in general, like you want to understand what are all the possible fundamental blocks of a G representation. And one way of solving this problem, or of not of solving, but of studying this problem, is by breaking up your representation, restricting this representation to a subgroup that is smaller, and in particular it has to be normal, but the important thing is that it is more tractable because the subgroup is smaller. And so if you want to understand a certain irreducible representation G from G, which I denote in this case by psi, restricting this representation to H, you can decompose this. This is a theorem, a classical result in the area, as a sum of these representations. The important part is that each appears with the same multiplicity, where all of these C sub I are irreducible representations of G, of H, I mean. So we are switching between G representations and H representations. And then understanding psi is equivalent to understanding each of the C sub i's. And there are two possible cases. You can have that k is equal to 1 or k is greater than 1. If k is greater than 1, you can recover this representation psi as an induction of an L representation, where L is between H and G. Since L is smaller than G, you can, this allows you to simplify the problem of studying this representation. But if k is equal to 1, you have to use projective representations, because psi is decomposed as a tensor product of two projective representations. In particular, P sub 1 is a projective representation of G quotiented by H. And P sub 2 is a projective representation of G. And so in this problem of classifying all possible representations, the notion of projective representations is unavoidable. And then recalling this connection between symmetric functions and representations, basically through the characteristic map, you can motivate this odd characteristic map. This is kind of the analogous notion for projective representations. So again, you take the values of your character, and you associate all the values of this character to a certain symmetric function. In this case, the scalars are different, but the idea is the same. And again, P sub lambda is the power sum symmetric functions. And something that is novel in the case of irreducible projective representations is that you have two types of these representations. like the positive and negative representations. The positive ones can be understood by basically using the classical representations of the symmetric group. So those are kind of very similar and not very interesting. So to classify all projective representations, which is the kind of natural question in this area, it suffices to understand irreducible negative projective representations. This is going to be enough. And if you consider the map from the previous slide, this odd characteristic map, recall that in the case of the Frobenius characteristic map, when you found the image of all the irreducible representations or the irreducible characters, you obtained the basis of sure functions. In this case, you are going to obtain Q sure functions indexed. I basically use this notation of Q sub lambda, so that in this context, the change of basis between Q sure functions and power sums capture all the information of the representations. And this is a bit more technical than in the previous context, and this theorem by sure kind of illustrates the difference, but morally, this is what's happening. And then P-sure functions can be defined as this scalar multiple of Q-sure functions. So since this previous discussion motivates Q-sure functions, P-sure functions are also motivated from this perspective.
Does even mean it has only even parts per partition?
Good question. I had a paper just in case I got this question because I always forget. So a certain partition is even if it is a product of disjoint cycles such that the cycles all have odd length. And so I guess by cycles, I mean in this case that all of its parts are odd in this case. So there is like a correspondence between partitions and permutations, and then you can think of, but yes, so I guess all the parts are odd.
Oh, so for like one, okay, so it has length of a cycle is 1, 2 will have length 2.
Sorry?
So it's the other way. So a partition lambda is even if it's, so in terms of parts, what is the characterization?
So yes, in terms of parts, it is even if all of its parts are this is counterintuitive, but if I am not mistaken, if all of its parts have odd length.
Interesting.
But
Okay.
yes, like the notation comes from the fact that you can associate to each of these partitions like a class of permutations, and using this from the side of permutations, this corresponds to all the permutations that have no cycles of even length.
Okay. Yeah, that's okay. Like the alternating group sort of thing.
And so this motivates P-sure functions. Although I think I gave like an intuitive idea, but this is a lot of this topic is very interesting. Like I feel it gets more technical, and we can discuss more about this at the question period if we want to go into more detail. For the rest of the talk, we will deal more with the combinatorial motivation of these functions. So now it seems that, sorry, you can associate to each of these, to each of the P-sure functions, a collection of the diagrams. This is very similar to the story for sure functions. So in that case, you found these kind of partition-looking diagrams. In this case, you have like these partition diagrams, but some of them are displaced. And the idea is that these are partition diagrams such that each row is displaced exactly 1 unit more than the row before. And so they are diagrams that look like this. The rule is very similar. So again, you want to fill this with integers in such a way that they are increasing in rows and columns, but the rows are weakly increasing, the columns are strictly increasing. The main difference between this and the case of the Schur functions is that in this case you can have like primed entries, so entries like 2 prime in item D, and basically you impose a certain order on these primed entries. The order is that the primed counterpart is less than the number itself. So 1 prime is less than 1, 2 prime is less than 2, and so on. And the rest of the order relations are the conventional ones. When finding the content of one of these diagrams to find the associated monomial, you treat the primed counterparts as though they had no prime. So for instance, in diagram E, we have 1, 2 prime 2, and the monomial corresponding to this is x1, x2 squared, despite the fact that one of them is primed and the other is not. And again, as you sum over all these diagrams, all these possible ways of filling these diagrams, you obtain the P-Schur function corresponding to this partition to 1. And so the main idea of the talk is to find a new combinatorial rule to describe the multiplication of P-Schur functions from a plactic perspective. But to be able to do that, I need to go back to the classical story and kind of understand the traditional rule for Yamanouchi tableau using the plactic monoid. And so let's consider first the multiplication of Schur functions. The coefficients c sub lambda mu nu basically basically appear in this multiplication. And there is a combinatorial way of understanding this multiplication that was sort of starts with Schoenstedt. And so Schoenstedt found an insertion algorithm to study. His original motivation was to understand increasing or decreasing subsequences of a given permutation. And the main idea is that for a certain permutation, you can recover the length of the longest increasing sequence, or subsequence, I should say, by understanding what is the length of the first row of this insertion diagram. Instead of using this notion of increasing subsequence, you can also, you can also study instead decreasing subsequences. And in this case, the length of the longest decreasing subsequence is the length of the first column of this diagram. And so this is original motivation for this algorithm. The way that it works is basically, let's say you have this diagram 2, 3, 4. You want to insert the element 1. Then you start by inserting it on the first row. The way that you do that is you see what is the greatest, what is the smallest element greater than 1. In the first row, that is 2. You place 1 in its position, you bump 2, and then you repeat the same process for 2 in the second row, and so on until you finish, and then there are no more elements to insert. And so this is an algorithm that comes from this notion of increasing sequences, but the reason that it ends up being relevant is because of the plactic monoid. And so basically there is a monoid whose elements are semi-standard Young tableaux, so these diagrams that we saw before that have a partition shape. And the way that you define a multiplication on this monoid is you multiply 2 tableaux by finding the reading word of the second tableau, and then inserting subsequently all its elements, all of those letters in the first tableau. So in this case, the multiplication of 4, 2, 1, 3 with 6, 5 is this tableau. And this is associative, so it's a monoid. And this monoid has a very interesting structure. So if you let S sub lambda, and this is different from the S we used for Schur functions, this is going to be a a similar version, but inside the plactic monoid. If you let this stand for the sum of all plactic classes that have this shape, so all of the semi-standard Young tableau having shape lambda, then there is an injection of the ring of symmetric functions inside the plactic monoid. And in this case, to make this a ring homomorphism, instead of considering the plactic monoid, which only has a multiplication, I consider the ring, so this ring that comes from taking the linear combinations of elements inside the plactic monoid, so that you have like a sum and a multiplication as well. If you consider this structure, the symmetric functions live inside the plactic monoid, and the most important property is that these elements that we defined inside the plactic monoid, this big S sub lambda, they commute pairwise.
Small question. So a plactic class is exactly what? The one that gives us the same sure function, sure monomial? Or
Good question. So a given plactic class is basically a semi-standard Young tableau. So one particular choice of that.
okay,
And then,
it is one. Okay. Okay, so it's not all of the semi-standard Young tableau that give us the same sure monomial, but just one semi-standard Young tableau.
yes. And then as you take a big S sub lambda, this is going to be the sum of all possible tableaus that have that shape. And then
Okay, cool.
okay, there is yes, the connection that comes from that establishes this bridge between the plactic monoid and the coefficients that we saw in the multiplication of sure functions is this result that you can find this coefficient by calculating all pairs of tableau, T sub mu and T sub nu. You can also think of these as all pairs of plactic classes, such that their product, so again, basically inserting the second tableau in the first one, is equal to T sub lambda, where T sub lambda is a fixed plactic class that has shape lambda. And the surprising thing, or one of the surprising features of this result is that you are free to choose any shifted plactic class of shape lambda, and the result holds holds at the same time. And so the way that you recover the classical Littlewood-Richardson rule is that you consider Yamanouchi words. And what is a Yamanouchi word? This is basically a word such that as you read it from right to left, you find always more i's than I plus ones. This is an example. So the word 3, then 2 to 2, then 4 times 1. This is Yamanouchi because as I read from right to left, at first I find more 1s than 2s, then more 2s than 3s, and so on. And the content of this Yamanouchi word is equal to a certain partition. Let's call it lambda. So something interesting, or the reason that they are very useful, is because as you find the insertion of the Yamanouchi word that has content lambda, this is precisely a tableau that has shape lambda. If you think of the original motivation for the insertion algorithm by Schoenstedt, this is a very natural family of words. So I feel many times these are introduced, but the motivation or the reason that they are kind of natural is not very well explained. If you think of this motivation of increasing and decreasing sequences, this is a very natural choice of words, basically because the increasing and the decreasing structure of these families very easy to understand. So if for this particular example you wanted to understand what's the longest decreasing sequence, what's the second longest decreasing sequence, and so on, it is very, very easy to find that in this case, if I wanted to take like the longest increasing sequence, for instance, then 1, 1, 1, 1. The 4 ones at the end are this sequence, and so on. So that is kind of the motivation for these words, as I can see it. And they are also very nice from the plactic perspective, because if you let T sub lambda, if you let this tableau be a Yamanouchi tableau, then this immediately forces T sub nu to be Yamanouchi as well. And that means that instead of counting all pairs of tableaux such that they insert to this particular shifted to this particular fixed tableau, you can fix a Yamanouchi tableau on the right, and then this forces a certain choice for the second factor, and it's enough to count all tableau T sub mu that satisfy this equation, this equality. And from this, I am not certain this might because there seem to be many papers about this, but from this equality, there is a proof of the ordinary Littlewood-Richardson rule for sure functions. And the hope here is that we can emulate this strategy in the shifted setting to find to prove like the existing shifted Littlewood-Richardson rule. And so to sort of follow this strategy, we need to find like a sort of plactic monoid for the case of projective representations. One way that I can try to generalize this is by understanding the plactic monoid to be this object that arises very naturally from an insertion algorithm. And then there is also like an algebraic way of defining it, but I think maybe the first motivation is more useful for this perspective. And for shifted diagrams, there is an insertion algorithm called the Haiman's mixed insertion, and this is kind of an intermediate between. So in the classical case, you can insert elements by rows, or you can insert them by columns. These are called like left and right insertion. Haiman's mixed insertion is kind of an intermediate, so it's a quotient of left and right insertion. And intuitively, like his idea is that each of these shifted tableaux, each of these shifted diagrams can be understood as a bigger diagram that is symmetric alongst the diagonal. And you can define a very natural insertion algorithm by inserting alternatively entries on the columns and the rows, depending on whether they are primed or not. So this is more difficult to define than Shenset's insertion, but something that sort of like recovers the connection with the traditional insertion is that there is again this connection between an increasing or decreasing statistic and the length of the rows of the diagram. So in this case, instead of using increasing or decreasing words, you want to think about hook subwords. A hook subword is a word that is strictly decreasing and then weakly increasing. And the length of the longest such word or subsequence in a certain word is equal to the length of the top row of the mixed insertion of that word. And so this seems like the most natural candidate for a plactic monoid in this setting. And there is a monoid that uses this algorithm. It is called the shifted plactic monoid. It was found by Serrano. The strange thing is that before we had like the plactic monoid being codified by two relations, and these relations involved 3 letters on both sides of the equality or the equivalence relation. This time we have 8 relations, and all of them have degree 4. So it is not very clear that this is the only way to sort of like generalize this to the shifted setting. At the same time, there are different insertion algorithms for the shifted setting. So apart from Haiman's, you have an insertion by Sagan and Worley, and also there is an insertion by Kraskiewicz as well. So it does not seem that this is like the right choice of a monoid for this setting. And then, so let's justify why this is the right notion for this context. So in a similar way to what we did for the plactic monoid, we let P sub lambda be the sum of all shifted plactic classes of a certain shape. Then if I let bold S be the shifted plactic monoid, there is again a ring homomorphism between shifted Schur functions and the shifted plactic monoid. Essentially, these elements commute pairwise. And again, I have a description of these coefficients, F sub mu nu to lambda. These are the ones that show up in the multiplication of two P-Schur functions. And so again, I have basically an identical rule. But let's say I want to understand why is this the right monoid to consider in this setting. And so one way to justify this is by seeing that the plactic monoid satisfies a universal property. It is the smallest monoid that satisfies that the inclusion map of the symmetric functions is a ring homomorphism. That once you let the letters in the plactic monoid commute, that this respects the equivalences defined in the plactic monoid. And if you take only the letters in an equivalence belonging to a certain interval, then the resulting equivalence of the restrictions on both sides, this is also an equivalence. And finally, if you take certain letters and which you can think as integers, and you change them for different integers in such a way that the relative orders of each of the pairs of these integers are respected, then this also commutes with the plactic equivalence. And this characterizes completely the monoid. Basically, the plactic monoid is the smallest monoid that satisfies all of these properties. You can think of this, so you may think that the smallest monoid is kind of unprecise. So in the paper with Oliver, we formalize this by saying that it is the initial object in a certain category, but this is the intuitive idea behind this universal property. This kind of more unprecise version was proved initially by Schützenberger, and in the paper we give like a categorical version, correcting like some of the mistakes that were part of the original proof. Now, for the shifted plactic monoid, a universal property like this was not known. And so you want to see if a similar set of properties is satisfied. Unfortunately, it fails. So for instance, in the shifted plactic monoid, this is true. For A, B, C, and D that are in the natural order, so A less than or equal to B, less than or equal to C, smaller than D. But if you restrict to this particular interval, you obtain the equivalence BDC equivalent to DBC, and inserting the left side, you obtain this tableau. Inserting the right side, you obtain a different tableau, the tableau in B. So this is not a property of the shifted plactic monoid. But there is a way to salvage all the construction or this idea. Basically, you can reinterpret the axiom saying that as you let letters commute, this respects the plactic equivalence. And you can instead think of a restriction map not to the completely abelian monoid, but to the plactic monoid. And you want this map to be well defined. And basically, if you exchange this condition by the previous condition, then all of these are satisfied in the shifted plactic monoid. But there is a kind of second difficulty that is less natural. So in the classical case, you had the partitions corresponding to rows, partitions corresponding to columns, and this condition that the symmetric functions had to commute pairwise was phrased in terms of these rows multiplied by certain boxes and so on. For shifted diagrams, there is a natural notion of row. So the partition that has a lot of boxes in the first row is still a shifted partition, but there is not a natural notion of columns because a column is not a shifted partition. So then you can impose certain rows to commute with a box, or you can impose a condition of staircases commuting with a box. These are kind of the two most natural approaches. Fortunately, both agree. And then in this case, I have 3 tables. The first 2 codify the relations you obtain in the case of imposing a staircase times a box to commute. And the second table, the last table, I mean, codifies this condition that a staircase commutes with a box. And if you cancel out all the terms in the last table that are redundant, then you obtain precisely the elements of the first 2 tables. So the two axiomatizations are equivalent. And this perhaps is a bit technical. All this says is that you can find like a similar strategy even for kind of special cases. But we obtained this result. So it was previously not known that the shifted plactic monoid also had a universal property. But if you take this set of axioms, the shifted plactic monoid is the smallest monoid satisfying all these properties. And in particular, this shows that this is a natural kind of candidate for the shifted setting. Once we have that this is indeed a natural candidate, of course, the natural question is to consider what is the kind of combinatorial rule describing the multiplication of Fisher functions. And the hope again is that we can recover using this perspective the rule found by Stembridge. And you might think, okay, so Yamanouchi words were kind of the starting point to obtain the classical rule. So why not consider Yamanouchi words for this context as well and see if they form a shifted plactic class and they satisfy the same properties. However, if you consider this same example that I had on a previous slide, you can show that this tableau that has a shape 6-2 can be expressed as the multiplication of 2 smaller tableaux, but the tableau in the second factor, so the insertion of 2, 2, 1, 1, this is not a word that has partition content. So this property that we saw before, that if a certain tableau on the right was Yamanouchi, then the right factor is also Yamanouchi. This is not satisfied in the shifted setting. And more than that, Yamanouchi words do not form a shifted plactic class. So depending on what Yamanouchi word you insert, belonging to the same plactic class, you may obtain different shifted tableau. So we have to think of a different candidate. And the main result here that gives a clue as to what is the natural notion for this context is this result by Serrano. So basically, the shape of the Haiman insertion of a certain word is completely determined by the hook subsequences of that word. So before we had that Schoenstedt insertion was completely, its shape at least was completely determined by increasing and decreasing subsequences. In this case, hook subsequences completely characterize the insertion. And so we said that for Yamanouchi words, this notion that they are kind of very transparent from this decreasing perspective motivates the definition of these words. So instead, I could consider words that look like this. So let's say I take a certain shifted partition, in this case 431, and I take the last part and index that with, so put a 1 for that part. After that, I see the second last part, in this case that is 3. And so I write this decreasing sequence that starts in 3 and ends in 1. Finally, I consider the first part and follow the same procedure. So I start by 4 and I write all the numbers until 1. Then this is a union of 3 decreasing sequences. Recall that Hooke's words are words that are strictly decreasing and then weakly increasing. So if I have a certain word that is very easy to understand from a decreasing perspective, so it has very, very easy to identify decreasing blocks. These decreasing blocks are also Hooke's words. And then this word has a very easy structure from the perspective of Hooke's words. But then again, the question is, do this insert to the right shape? And we found using semi-standard decomposition tableau that if you insert these words for any partition, they indeed have the kind of desired shape. And we call these words Berli Yamanouchi, and they are because of their connection with Yamanouchi words. And so we said that Yamanouchi words do not satisfy the right factor property, but maybe Berli Yamanouchi words are different. To answer this question, it is useful to kind of characterize them using a very similar kind of condition to the Yamanouchi condition. So the Yamanouchi condition is you have more I plus ones than i's as you read from right to left. You can characterize being Berli Yamanouchi by by being a certain word that as you read from right to left, having either the same number of i's and I plus ones, or having exactly one more I than the number of I plus ones. And then if you have, so maybe, then if you have a particular word that is Berli Yamanouchi, it follows that a right factor is also Berli Yamanouchi. So if a certain long word satisfies the Berli Yamanouchi condition from right to left, as you read a smaller section of the word from right to left, then it also has to satisfy this condition. And a stronger result is true. Not only is the right factor Berli Yamanouchi in this case, but it is Berli Yamanouchi of the appropriate shape. And perhaps just as an example of this class of words, 7, 6, 4, 5, 3, 4, 2, 1, 3, 2, 1 is Berli Yamanouchi, but the second word is not Berli Yamanouchi, because as you read from right to left, you find a 3, so the first 3 from right to left, but then you find a second 3, the 3 that is in red, and there are 2 3s, 2 instances of 3, but there is no 4. So the number of 3s and 4s do not satisfy the Berli Yamanouchi condition at the point of the 3 that is in red. Okay, but then for Berli Yamanouchi words, we have the right factor property. So the hope is that counting the tableau T sub mu that appear as left factors in this product, we can recover the rule by Stembridge. So we want to read these left factors, but it seems that they are very difficult to understand. So it is very difficult to read this tableau or to find like a certain word that inserts to one of these tableaux. In general, a notion of reading words for Haiman's mixed insertion is not known, and this special class is not better in this respect. And so we have to find a way to solve this. Maybe there is like a smaller class of tableau that we can read, and hopefully in such a way that we can still count the coefficients. And to motivate this class of words that solves this problem, I consider the notion of shrinking sequences. So a shrinking sequence or a shrinking block of composition is obtained by taking the greatest element in the word, in this case 7, decreasing by 1. So you append to the sequence 6, then 5, then 4, and so on, until you get to 1 or until you can find no more integers. Then you repeat the process with the longest element of the remaining letters. So in this case, the longest element would be 4, and you continue with 3, 2, and 1. So that in this case, you have two blocks, the blue block and the black block. Each of these blocks is called a shrinking sequence. And then I say that a certain word is interlacing if an instance of I in the jth shrinking sequence is left of an instance of I plus 1 in the j minus 1 shrinking sequence. And this notion is useful because tableaux that are inserted from interlacing sequences are easy to read. But again, the problem is that since we decided to take a smaller class, so we wanted to characterize scarcely Yamanouchi words. These are the words that appear as left factors. And since that is very difficult and we restricted to interlacing words, it may be that interlacing words do not exhaust all the elements that can show up as left factors. And there are examples of words that can appear as left factors and that are not interlacing. So the class of scarcely Yamanouchi words is bigger. But there is a miracle. This is really like the idea that makes all the project work. And is that if you choose a particular right factor, you can guarantee the left factor to be interlacing as well. This means that you can count the structure coefficients of visual functions using interlacing tableau. And so I said that interlacing tableau were easy to characterize combinatorially. By that I mean that all of these tableaux can be constructed in this manner. So basically, you lay down successively vertical strips of unprimed entries and then horizontal strips of primed entries, increasing the vertical strips from top to bottom and the horizontal strips from left to right, in such a way that the horizontal strips consisting of primed entries are right of the vertical strips corresponding of unprimed entries, and such that none of these sequences or none of these vertical and horizontal strips can be extended. I will explain later what extended means. But to give an example, yes, if I take these partitions, these partitions lambda, mu, and nu, then the tableau in A, B, and C are valid constructions, basically because I place first the 1. This is a vertical strip. Then I am thinking here of the tableau in A. So then 2 prime, this is in a horizontal strip. It is right of the vertical strip. Then the second sequence is when I append this 3. This is a vertical strip, and 5 is a vertical strip as well. Maybe an example that is more clear for this construction. So if you look at the tableau on the left, then as you see the black sequence, it has a vertical and a horizontal strip, and the horizontal strip is right of the vertical strip. Then the blue sequence is on top of the black sequence, and it has also a vertical strip and a horizontal strip in such a way that the primed elements of the later sequence are below the primed elements of the previous sequence, and the unprimed elements of the blue sequence are right of the elements of the black sequence that are unprimed. Again, for the red sequence, you follow a similar procedure. You append a vertical strip and then a horizontal strip, and the tableau that can be obtained in this way are interlacing. This last condition that was kind of mysterious, this condition that a certain tableau cannot be extended, this means that when you compare these two tableaux on the slide, you can see that the tableau, that the 10 prime that is in red is right next to a 9 prime that is in blue. So basically, if you start at the biggest element of the last sequence to be constructed, and you go back by columns and then by rows, you should not be able to use elements from a previous sequence that are like immediately below those elements. So in this case, a different way to say it, maybe more clear, is that you want to obtain certain tableau that can be constructed in a unique manner. And in this case, if you take the tableau on the left, this can be constructed in 2 ways: by regarding 10 prime as an element of the red sequence, or as an element of the blue sequence, as you can see from the 2 tableaux side by side. So interlacing tableau are tableau that can be constructed in a unique way. And the reason that this characterization is helpful is because once we have all tableaux that satisfy all of these properties, for these partitions again, there are only 4 tableaux we need to consider, and the last one is not valid. So in this case, the coefficient is equal to 3. But if we had to use the classical rule by Stembridge, there would be, for this case, 8 tableaux, and some of them invalid. So in general, we have to consider less tableaux, and checking these conditions, whether the tableau is valid or not, is also easier. So I guess the surprising thing is that despite using like this very natural notion of Bernoulli-Manucci words, and obtaining like a rule that seems to involve less tableau and easier checks on each step, this plactic perspective in the shifted setting does not recover the classical rule, but we obtain a new one, and it seems that this one is faster. At least you have to consider less tableau in general. And maybe I finished a bit early, but that's it. Thank you very much for listening.
Perfect. Let's thank our speaker. Anyone have any questions they'd like to ask? You can type them in the chat now, or you can just unmute and ask. Yeah, Yannick, go ahead.
Hi, Santiago. Thank you very much for your very nice talk. So you mentioned that with Olivier, you rewrite Schützenberger's axioms of the plactic monoid in a categorical way.
Yes.
So if I understand well, the plactic monoid will be an initial object in a certain category.
Yes, exactly.
And same thing, I suppose you have an analog result for the shifted plactic monoid, right?
Yes, exactly.
So, okay. My question is, do you have another categorical interpretation of combinatorial operation on the plactic monoid and the shifted plactic monoid? For instance, can you realize in a categorical way insertions, looking for biggest increasing words in a subwords in a class of a tableau, for example? Those kind of ingredients that usually appear in the study of plastic and shifted plastic monoid. Can you realize it also in a categorical way?
Yeah, that's it's funny because that was the question I had initially. So like for Haiman's mixed insertion, it seems that it is like a super arbitrary algorithm. Like you have to make like this quotient of left and right insertion, and there are like 3 insertion algorithms for the shifted setting. So it is far from clear that this is the right one. And I wanted to categorify like insertion or make sense of insertion categorically. And the best that I could do was to choose was to prove that the monoid defined by Haiman's insertion is universal in a similar way that the plactic monoid is universal.
I
But
see.
I have wanted for a long time to also categorify this intuition about increasing sequences and decreasing ones, and that seems more difficult. So this is a very interesting direction to pursue.
Okay, thank you.
Thank you.
I just wanted to know if there's a plactic monoid for Sagan and Worley stuff. Like-
Sorry?
Do other insertions also have known plactic monoids like Sagan and Worley? Like I can do some algebra stuff to encode it.
So in the case of Sagan and Worley, it is very interesting because you can think of each of the insertion algorithms for the shifted setting as capturing a different aspect of traditional insertion. So in the case of Schoenstedt, on one hand, you have this combinatorial connection to increasing sequences, and that is captured by Haiman's insertion. There is a different notion that is, or like a different aspect of this insertion algorithm, and is the fact that you can define a monoid. This is also captured by Haiman's insertion in a certain sense. But then, like, you can also think that there is a motivation for the classical algorithm that comes from the fact that that it is like very natural, like this operation of inserting elements on the first row and considering like what is the biggest element and so on. And this combinatorial way of inserting is the one that Sagan and Worley generalize. So like the most natural one, like a priori, seems to be like the insertion by Sagan and Worley. But the problem is that that insertion is not well defined, because you can take different representatives of the same class, so different words that insert to the same tableau, and if you multiply them by different elements corresponding to a second tableau, they give different results. And that is very strange, because this is the most it is the most natural algorithm, but for some reason like this does not come from a plastic structure, or does not like give a plastic structure eventually. You can also ask like if this monoid has all the properties that the monoid in the classical case had, and the shifted one seems to carry seems to capture all the properties that the plastic monoid did. The main difference is that in the monoid, in the plastic monoid, there is this way to understand rectification in a plastic way. So there is a way to define like skew functions and a certain operation that makes sense of rectification. This is the only property that does not exist in the case of the shifted plastic monoid. So like it seems to suggest that maybe despite this being like a very good generalization, maybe there is like a kind of intermediate insertion that uses like a bit of Sagan and Worley and a bit of Haiman to define a different structure. So yes, I am very interested in seeing like if a different insertion can give a plactic structure, but so far only the shifted plactic monoid is
Interesting.
successfully capturing these properties.
Yes.
Thanks, Santiago, one more time.
Thank you.
And then I'll go ahead and stop the recording.